Hello, welcome to Apologetics 101. I'm your host, Christian apologist Brian Keith Bowen. Today we have a special guest speaker, Dr. Jason Lau. He's been on this channel several times now, once already in the Genesis series, which we're doing the Genesis series part 9, I believe. And we're going to be discussing distant starlight, the so-called distant starlight problem, and as well as Dr. Jason Lau's ASC model. And we're starting right now. Well, hello. I am with Dr. Jason Lau once more on the Genesis series. We've been doing a series on the Book of Genesis, commentary series, where I would do an exegetical commentary on a particular chapter, and I go back and do a bunch of topological stuff. We're still in chapter 1. But Dr. Lau has joined me on today to talk about distant starlight. You've been really busy lately.
I have, yes.
Yeah.
It's all good though.
Right. So I'm glad you had this interview with me today. All right, I guess we can go ahead and jump in. Oh, well, do you want to introduce yourself? I know that lots of people know you, but do you want to go ahead and introduce some and tell some briefly stuff about you and your ministry?
Sure, yeah. I'm Jason Lisle. I'm an astrophysicist. Most importantly, I'm a Christian. The Lord saved me when I was very young, and I'm very grateful for that. I went into physics and astronomy, double majored in that in college, and then got my PhD in astrophysics at the University of Colorado in Boulder, and went into full-time ministry after that. Basically, apologetics ministry, the defense of the Christian faith, showing people that God's word is true from the beginning. And since I'm a scientist, I specialize in showing how the science lines up with Scripture. You don't need to bend Scripture to match what secular scientists teach. If you just look at the evidence, it's consistent with what the Bible teaches. And my specialty field, of course, is astrophysics.
Awesome. I was going to ask if you wanted to present your academic credentials on this, so they know that you are a physicist, and this is your area of specialty, and you're very interested in, and we're going to be talking a little bit today as well about relativity, and that is something that you're very passionate about.
Yes, in fact, I've written a book on it, The Physics of Einstein, and we stock that at our yeah, there it is. Yeah. So so we have that at our ministry. I should mention I'm the founder and president of the Biblical Science Institute, and I published that book. We have that on our website. You go to biblicalscienceinstitute.com. You can get The Physics of Einstein. I've always thought that was fascinating. I first read the details of Einstein's special theory of relativity when I was I think I was in 8th grade. And I just thought it was mind-blowing. And as I've studied it more over the years, and I've tried to communicate it in a way that I think laymen can understand it, it's a wonderful branch of physics. It's my favorite branch of physics because it's kind of abstract and counterintuitive. But in my opinion, it solves the distant starlight issues. So,
And it's also something that a lot of people don't have a whole lot of knowledge of, and so it kind of confuses people sometimes. And from what I understand,
yeah.
yeah, from what I understand, I've read this from several sources, including you, that it kind of works counterintuitive to what we normally think, because normally we think in Newtonian physics, and then we hear about relativity, and all of a sudden it just kind of flips it on its head, what we think reality is supposed to be.
Exactly. Yes.
Awesome. Okay. Today we are going to be talking about the so-called distant starlight problem. And before we get into the ASC model that was designed by, or the model itself was designed by Dr. Jason Lau, the ASC that we're going to get into, Anisotropic Synchrony convention, is something that goes back to Einstein, and we'll talk more about that in a little bit. But I do want some general consideration because we are talking about the so-called distant starlight problem. So we're going to go through some solutions that people have tried to come up with and that sort of thing, including I'm going to probably start it off with the one I think is probably the weakest argument, and we'll start it off there. But before we do that, I do want to ask a question of you, Dr. Lau. What can you define where the problem is? What people think is the distant starlight problem?
Yeah, basically the starlight problem, as many people see it, it's an objection to the biblical timeline, because the Bible indicates that God created the universe in 6 days. Earth's made on day 1. Most of the universe made on day 4. And we see these distant galaxies. We've measured the speed of light, and we know it's fast, but these galaxies are so far away that even at the speed of light, it should take an enormous amount of time for the light to get from there to here. Now, light's fast. It can go around the Earth 7 times in 1 second. It's fast. But these galaxies are so far away that you would think that it would take even billions of years for the light to get from there to here, if you're thinking in terms of Newtonian physics. And so that's where the relativity comes in. So basically, it's an argument against the biblical timescale by pointing out that we see these galaxies indicating the light has gone from there to here. We see it. And since it would take billions of years for the light to do that, doesn't that prove that the universe is billions of years old? It's an argument that's often used by laymen, people who are not scientists or are not specialists in relativity, because I have to tell you, I've never heard anybody who's an expert in Einstein physics make that argument, because they know better. It's not a good argument, but it sounds very simple, and so it's very persuasive to people who are not well versed in the physics of Einstein.
I've heard that Hugh Ross tried to make that kind of argument, but he's not a physicist nor an expert at relativity.
He does have a PhD in astronomy, but I don't think he's all that knowledgeable of relativity, because I've seen him make mistakes in that area. So
yeah, and I watched your debate.
I haven't heard any other astrophysicists make that argument. They know better.
I watched your debate with Hugh Ross on Revealed Apologetics too, where he kept making mistakes on that as well. But we'll get into this in a little bit. But basically, this distant starlight problem seems to assume the ESC model, right? The ESC, the convention, right. Yeah, that it's consistent both ways, or the same in both directions. What's also called the Isotropic Synchrony convention, or the Einstein Synchrony convention, and use both ways and that sort of thing. Actually, I really prepped myself for this interview. I did an interview with Eric Hovind last Friday, and I got managed to get that to upload it to YouTube by Saturday. And ever since then, I just basically crammed myself in just about everything you've written on the topic matter. I've read your peer-reviewed journal article. I will link that in the description box below so everybody can see that you wrote a peer review, and it was peer-reviewed on Answers Research Journal. Is that correct? And I'm going to include that link in the description box below. And I read that. I read what your response to Peter on your Biblical Science Institute. I read some stuff that you wrote on the distant starlight issue on there. Also, I've seen discussions that you've actually made on this topic matter, as well as your video review of that debate that I mentioned that you were in with Hugh Ross on Revealed Apologetics as well. It is also found on your Biblical Science Institute. So I've really prepped myself. Also reading several chapters relevant to this discussion in your book, Physics of Einstein. So hopefully I can come away sounding like I know what I talk about. So, but I really prepped myself for this interview. So, but I did actually took the time to read what you've written on the subject matter. All right, there has been over time some possible solutions that people have raised up. And I want to get your insight onto these other issues that raised. Now, the first one is why I consider it to be the weakest of the arguments. I don't consider this to be very strong. I don't think you will either. But obviously, light in transit. So, what do you think on that?
Mm-hmm. Yeah, so that's the position that some Christians would profess. They would say, well, the reason we're able to see those galaxies is not because the light actually got from there to here. But God, when he made the galaxy, he made a beam of light connecting it from the galaxy to the Earth, to our eyeballs, whatever have you. And sometimes people will confuse that with mature creation. They'll say, well, God created Adam as an adult. Yes, he did. There's no doubt there. But there is a difference between God making a human being functional from the beginning and God creating a beam of light with pictures in it. Because it's not just that we see light when we look out into space. We see galaxies. We see actual images of things. And if God had just made the beam of light with pictures of that galaxy in it, then we haven't actually seen any galaxies other than a small portion of our own. And so that's a bit of a problem, especially when we see things happening in space. And this is the real killer. This is the thing that convinces me that the light in transit is not a good solution. We see stars blow up occasionally in space, and some of them are farther away than 6,000 light years. Now, a light year is a measure of distance, but theoretically, you would think it would take light 6,000 years to travel 6,000 light years. That's how the unit gets its name. And so we saw a star blow up in 1987, and it was in one of the Magellanic Clouds. It's 168,000 light years away. Now, if you say, well, the reason we're able to see that star and see it explode is because God made a picture in a beam of light of that star that was about 6,000 light years long, and then pictures of an explosion that never happened. You see, if light in transit's true, that star never existed, and that explosion never happened. It was just pictures that God made in a beam of light. And no one denies that God has the power to do that. That's not the issue. Is it consistent with God's nature to make beams of light with fictional images? And if you say, yeah, I think it is, then you've just lost all contact with reality, because you don't know that I'm speaking right now. You say,
Would you
well,
consider that,
the pictures of you, well, God created the beams of light. Say again?
Would you consider that if someone claims that, then that's equivalent to claiming that God is able to create these deceptive images of things that never actually happened, that he would be capable of deceiving? And I think I've actually heard that you've even taken it one step further and say that, then how do you know that, like you and me are actually having a conversation in a few minutes, maybe this was created, So in retrospect, but it doesn't follow logically, and so that's one of the biggest problems I had is I mean, there's some scientific issues, but biblically it would make God out to be a liar. It would make him creating pictures in the sky that never actually happened, and we actually see, like you said, we see stars blowing up, moving around. All right.
Right. If nothing changed, I might be a little more inclined to accept that as a possibility. But the fact that we see stars explode and things, do I analyze that? Is that something that's real, or is it just a picture that God made for our benefit? No one denies God could make fictional movies if he wanted to. I just don't think he does. It's not consistent with his nature. And by the way, some people will try to counter that, and they'll say, but wait a minute, God created Adam with appearance of age. And I would say, no, he didn't. He made Adam as an adult, because you got to start somewhere, and it wouldn't make sense to start with a baby that can't care for itself. So God started the universe in a particular condition. But Adam looks old. No, he doesn't. He looks the way he looks. People assume that there's this appearance of age, which is really a reification fallacy, because age doesn't literally have appearance. Yeah, age literally doesn't have appearance. We use it sort of informally when we say a person looks a certain age, but what we really mean by that is that person has physical characteristics that are typical of a person of a given age. But Adam wouldn't be that way. When he was first created, his true age is 0. And yet he's an adult. And we know today it takes time to get there. So that's in a different category from God making pictures of things that never existed and events that never happened.
Yeah. When reifications are used in non-figurative ways, that's acceptable. But when we use reification in a logical argument, meaning we're trying to persuade somebody that something is true or false, then it becomes a fallacy in logic.
Reification of itself is not a problem, but when you use it in part of an argument to overcome a problem, that's a fallacy.
Yeah, most young Earth creationists today don't use the term appearance of age. They use maturity of age or mature. That the idea is that they created them fully functioning. Appearance of age seems to suggest, one, that God is deceptively making him look old when he's not, and two, it becomes a fallacy in logic the way people might be using it.
Yep.
But obviously that would be a big difference in creating light in transit, as you mentioned.
I believe there's a fundamental difference between those two categories. Yeah.
Next, here's one that sometimes comes up. Some young Earth creationists try to challenge starlight distance. You mentioned something about that these things are billions of light years away. How do we know that they're billions of light years away?
That's a good question. If you want a sort of general answer, I'd recommend to viewers that they Google the cosmic distance ladder. And the reason, see, we actually use multiple techniques to get the distance to things, to estimate the distance to distant objects. And the range of distances in space is, well, it's astronomical. And so there's no one method that works over the entire range from the moon, say, to the most distant quasar that we can detect. But there are multiple methods we use and they overlap. And so that's good because that means we can calibrate one method based on the previous one. For relatively nearby objects, well, for really close objects, we can use things like a light or radar. We've bounced radar beams off of Venus, and we've been able to measure the time of that beam, and then it gets you the distance because it's a round trip. So you can measure the distance that way, very precisely. The distance to the moon we can measure with a laser, and in timing that we know the distance to the moon within a fraction of an inch even. So it's really precise. Nearby stars, we use parallax. And parallax is basically the same way that your eyes work if you have stereoscopic vision. You might notice when you put your finger out like that, if you blink your eyes left and right, your finger will seem to shift relative to the background objects because your finger's closer and you have two different angles on it. Now, that also happens to stars that are nearby when the Earth's on one side of the sun, that's like your right eye, versus when the Earth's on the left side of the sun, that's your other eye. And so nearby stars will shift a little bit relative to background stars. And this has been detected. This is called parallax. And we can detect that with Earth-based telescopes for stars within a few hundred light years. And then with spacecraft, we can go way out because spacecraft, they don't have the blurring effect of Earth's atmosphere. And so the Hipparchus mission pushed it out to about 2,000 light years. And now we have the Gaia mission, which it can measure the parallax of stars out to a distance somewhere close to the center of our galaxy. So that's like 30,000 light years. So that gets you that, but that's just a fraction of our galaxy. So but those stars can be measured directly using, that's just geometry. If you've had high school geometry, you know how to do parallax. And that goes way beyond 6,000 light years. And so anybody who's saying, no, the universe is actually really small, even one of the closest methods we use goes beyond that. Now, beyond that distance, there are other methods. There are called standard candle methods. I really like these. Standard candle is basically, if you had a candle close to your face, it would look quite bright. If you had a candle on a mountaintop at night, you could barely see it. It would look much fainter because of the distance. So if you know the brightness that the object actually has, its intrinsic luminosity, and then you know how bright it looks, you can calculate the distance. And because light, the brightness of an object drops off as the distance squared. And so if an object's twice as far away, it'll look 1/4 as bright. And there are certain stars that we can identify that pulsate in a particular way, and they have a certain known luminosity. And so by knowing the true brightness of the star, and then by measuring how bright it appears in our sky, we can calculate the distance. And you can use Arillary stars for that, or Cepheid variable stars. In both cases, we know the true brightness of the star. We know, because some of them are within the distance where we can measure the parallax. So we know the true brightness of it. And then we can measure the apparent brightness, get the distance. There's other methods too. There's the moving cluster method. There's the type 1a supernovae, which is actually a standard candle method. And those will go out to enormous distances. And by the time you get out to the farthest galaxies, the main method we use is redshift. Galaxies that are farther away tend to be more redshifted than galaxies that are nearby, which means the frequencies of their light have been shifted to longer wavelengths. And it doesn't necessarily mean the galaxy looks redder, although it might at extreme distance. So those are some of the methods that we use. They're good logical methods. They're not based on any kind of secular or evolutionary or long age assumptions. They're based on geometry, logic, math. So they're good methods, and they get less precise as you go farther out, but they're still accurate. So the universe really is as big as astronomers claim it to be.
When I first heard about parallax, parallax is probably the most commonly known and mentioned. Some people mention it so much that they think that's the only method that they use. They're not aware of the other methods. But I always thought that was an ingenious way. I was like, wow, that's actually pretty clever. But some people like Kit Hovind would challenge it, looking at a point, and I don't know how he describes it and stuff. But you would probably say that it does have a limit. That's why we use these other methods for further out. But even taking parallax as far as you can go with it accurately, it would still be beyond 6,000 light years. That's how you would argue on that as far as parallax. So you would see this as really a solution.
Today. Now that wouldn't have been that wouldn't have been true 20 years ago. But because the technology hadn't developed to the point, with the Hipparcos spacecraft could do parallax out to about 2,000 light years, and that's within the 6,000. But with the Gaia spacecraft, we can go out to like something like 30,000 light years with parallax. It's that precise, and it can measure the shift of the star that precisely. So parallax today can go out to tremendous distances.
Awesome. All right. Okay. This is one, it doesn't get brought up very much today, modernly, but people have suggested that the possibility of light taking shortcuts. Do you understand what the argument's on that? I don't know that much about it.
Yeah, and part of the issue there is, well, there's a lot of issues with that. There's a lot of issues with that. If it takes a shortcut, is it changing its direction? If so, wouldn't that distort the appearance of things? I mean, if you're going to take a shortcut, because normally the shortest distance between 2 points is a straight line, and that's pretty well the way light travels, unless there's an enormous gravitational field that's going to bend it a little bit. So there isn't any shorter distance. You can invoke other dimensions and things like that, but it gets very, very speculative. And I'm wondering, if you took some different path, wouldn't that distort the appearance of things? And there's just no evidence of that. As far as we can tell, light travels in a pretty much straight line, other than the slight effects of gravity.
I used to drive a truck, and we went through truck driving school, and so we had to learn how to read a map. And that's the first thing they teach us is the closest thing between 2 points is a straight line.
Yeah.
All right. All right. Challenging the speed of light. Now, of course, we're going to talk a little bit more about the speed of light here a little bit in ASC on the one-way speed of light. But essentially, when they're challenging, this is also known as the C-Decay theory, where they claim that maybe the what we normally measure, which we can, as we're going to see, we can measure the two-way speed of light, the round trip speed of light, and they're saying that maybe over time that is decayed. And sometimes they even quote laboratory experiments where they've sped up particles, like with particle accelerator, faster than light and stuff like that. Maybe you know a little bit more about all that.
Yeah. Okay. So the C-Decay idea, and when I first heard about it, I thought, yeah, that makes sense. It's basically the idea that the speed of light was much faster in the past. And so you might say, well, today, yeah, light would take 1 billion years to get from there to here. But in the past, maybe it took only 2 days to get from there to here. So the idea was that the speed of light was much faster in the past and has slowed down for whatever reason. And I'm glad that somebody looked into that, because often it is the answer when a secularist proposes that some process necessarily takes a long period of time, a canyon to be carved or whatever. They're assuming that the rates have always been constant throughout history, when there's good evidence that they haven't been. The worldwide flood caused a lot more erosion than takes place today, and it did that in a year. So could the speed of light be like that? I think that was a good thing to try, but we have really compelling evidence that the speed of light in vacuum has always been pretty close to what it is today. And there's multiple lines of evidence for that. But I would point out, too, we got to be a little bit careful here. When we talk about the speed of light being constant, it is in vacuum that it's constant. In vacuum, the speed of light, the round trip speed of light, which we'll come to later, is 186,282.397 miles per second. and nothing changes that in vacuum. Now, when light goes through a substance, it slows down. Light is slightly slowed through air. It's slowed substantially in water. It's only like 75% its speed in vacuum in water. Okay, so the speed of light can be slowed down when passing through a substance, but that's not what the C-Decay idea is about. The idea of C-Decay is that the speed of light in vacuum was faster in the past. And so there have been laboratory experiments. Go ahead.
Well, I think you were
sorry, I didn't
answer it.
Because there have been laboratory experiments where they've slowed the speed of light down to like the speed of a bicycle by creating clever substances that will do that. That's not what we're talking about. We're saying the speed of light in space may have been different in the past. That's a neat idea. There's no evidence for it, and there's evidence against it. And granted, I've heard people say, no, historically, if you look at some of the older measurements of the speed of light, but if you take into consideration the error bars on those measurements, it's pretty consistent with the modern value. There is a phenomenon in science called tracking, where people will only publish an answer that's consistent roughly with the previous answer. And so there have been slight changes in the measured speed of light, but today we can measure it so precisely. In fact, in my junior lab, that as an undergraduate, I built an experiment that measured the speed of light. And that was kind of a neat thing to do. But we can measure it with modern equipment to just, very, very precisely. And it hasn't changed. In the decades where we've been able to measure it very precisely, it hasn't changed one little bit. And so it would be odd to say, well, it was slowing down in the past, and then just about the time we could measure it, it just locked into this current speed. That's a little problematic. The other thing, too, is that the speed of light we're going to find is very different from other speeds. It's a maximum speed. Nothing can reach or pass. Well, nothing with mass can even reach the speed of light. And anything that's massless has to travel at the speed of light. And it's an upper limit on speed, and it's tied in with other things in nature, like the strength and the relationship between magnetic fields and electric fields. You might have taken, maybe when you were in one of your science classes, you take a coil of wire and touch it to a battery, and you make a little magnet. It'll pick up a nail. It's pretty neat because there's a relationship between the electric field and it's a changing electric field, which produces a magnetic field, and so on. Those two are related by the speed of light.
I remember using a potato.
If you change the speed of light, it changes. Yeah, right. That can make electricity chemically, but there is a relationship between the electric fields and magnetic fields. It's based on speed of light. The other one that's really profound is the relationship between mass and energy. Mass and energy are related by the speed of light. That little equation of Einstein's, E equals mc squared. E is energy, m is mass, c squared. The c is the speed of light. And you square that, and that gives you the relationship between energy and mass.
I have a question.
Now, what that means is if this, yeah, go ahead.
Well, some people say that certain constants are certain. How anthropic principle and that sort of thing. There's certain constants. I think on relationship of electrons or something like that. I don't remember exactly, but there are certain constants that may be affected if the speed of light was any different than what it is today. Would you be able to elaborate on that?
Yes. One is the relationship between energy and mass. And so if the speed of light changes, let's say it drops, then since E equals mc squared, that means energy either has to drop, the energy of everything in the universe would have to decrease, which means the Earth's kinetic energy around the sun would have to decrease and it would fall into the sun. Or mass could increase to compensate for C decreasing, in which case the mass of everything in the universe increases, which means the mass of the sun increases, its gravity increases, and the Earth falls into the sun. And so either way, if you change the speed of light, as far as I can tell, if you were to slow down the speed of light in vacuum, if you could change that, the Earth would spiral into the sun, and that's not good. We don't want that. So that would be one example of that. There are other the size even of an atom is determined partly by the speed of light, because the electron wave has to be self-consistent, and its upper limit speed is determined by the speed of light. It approaches the speed of light in the way that it orbits around an atom. So the size of atoms would change if the speed of light changes, which means in some chemistry is dependent on the size of the atoms. And so even chemistry would potentially be very different. And so I'm concerned that if the speed of light were very different from the modern value, and I don't know how much, 10%, 20%, but if it's too different from the modern value, I don't think matter would be possible, at least not the kind of matter that we have. So that's one example of that. We don't know for sure how the speed of light is related to certain other forces, like the strength of the strong force and maybe the fine structure constant, things like that. There are lots of these constants in nature, and there's different speculations on how they relate to each other, but the speed of light may affect those as well.
All right. The final solution that I want to talk about before we get to the ASC model is one that was designed by a colleague and a friend of yours, Dr. Russell Humphreys, called White-Hole Cosmology, Gravitational Time Dilation. Now, of course, you talk about time dilation also with ASC. Exactly what is gravitational time dilation? What is his argument? And why don't you think that's what do you think that's a viable solution to the so-called distant starlight problem?
Okay. When he first came out with it, I thought, yeah, that might be the answer. It's pretty clever. And it got me thinking in the right direction. So I certainly appreciate Dr. Humphreys and his contributions, not just in that field, but in other branches of physics where he's shown how planetary magnetic fields confirm recent creation, things like that. Yeah, there's the book he published on it. I've read it. It was a neat idea. And gravitational time dilation is true. It's something that Einstein predicted. It's something we can now measure. Basically, clocks that are closer to a source of gravity, like the Earth, clocks that are closer to the surface of the Earth tick slower than clocks that are farther away from the Earth, all other things being equal. So, for example, just north of here, we got Boulder, Colorado. There's an atomic clock in Boulder, Colorado, and it ticks slightly faster than a clock of essentially identical construction that's at sea level at I think it's the Naval Observatory. They have an atomic clock there, and they're off by a little. They synchronize them both, at the beginning of the day, and at the end of the day, there's a little difference because the clock at sea level ticks a little bit slower than the one on the mountaintop. So the closer you are to gravity, the slower time goes, and it doesn't matter what the construction of the clock is. All clocks are equally slowed. And so what Dr. Humphreys proposed is that perhaps the number of galaxies in the universe is finite. And so that imagine a big sphere with galaxies all throughout it. And maybe we're near the center. We don't have to be exactly in the center, but if we're close to the center, then that would mean we're in a gravitational well, because it would take energy to pull something away from that because of the gravity of all those galaxies. If that's the case, clocks will tick a little slower on Earth than they do in those farthest galaxies. And that is a true principle if the number of galaxies is finite. Now, it won't work if the number of galaxies goes on forever, okay? Because then there's no well. But if the number of galaxies is finite, and we don't know that it's not, we don't know if they're infinite or finite. We don't know at this point. So that's one untested assumption. But and the qualitatively, it's sound. It's a neat idea. It's just when I work through the math, what is the difference between clock rates here and at the edge of the universe? If assuming the number of galaxies is finite and that they taper off to kind of where the limits of our instrumentation. And it's a small effect. It's like 2%. And that's including things like dark matter. So basically, yes, clocks potentially could tick a little slower on the Earth, but it's not enough to get the light here in the time required, because we need to get light to travel billions of light years within 6,000 years. And a 2% effect that would, instead of taking 10 million years to travel 10 million light years, it would take 9.8 million years. It's in the right direction, but the effect is very, very small. And so when I worked through the math on that, I decided, no, that's not going to do it. It was a neat idea. I'm glad Humphreys came up with it. And it got me thinking in terms of, well, relativity being the answer. So it was a neat thing to try. I don't think it quite works, but what a clever idea. Right.
And from what I understand from your debate with Hugh Ross, moderated by Frank Turek, you said that you have actually mentioned this to Dr. Humphreys about your concerns and issues with his view. So,
yeah, and by the way, the book that you held up, Russ Humphreys doesn't hold it. He doesn't hold to that view anymore.
You don't?
He doesn't. He moved on to a second. Yeah, he doesn't hold to that model anymore. He moved on to a second model, and he's now on a third model, which I admit I don't completely understand his third model. So But that's fine. We need competing models in science. That's how it progresses. We need to see which one makes the best predictions.
He abandoned the white hole cosmology model.
Yeah,
okay, good, because that's one of the major problems I had with it, because I wasn't sure, because it didn't sound very biblical. A whole universe starting out like a white hole, and and that sort of thing. But I can understand why that would work in theory, but it in practice, I just couldn't see it. But I heard that he has tried to defend his math on it. I don't know if Hugh Ross and you are both talking about the same thing when y'all have an issue with his math. Y'all might be talking about something completely different. But
well, yeah, his new stuff. He hasn't really promoted the white hole stuff in, I think, a couple of decades. Really, he's been working on a new hypothesis. He's shared it with me. I think it's got its issues too, but we've chatted online about it. And next time I see him in person, maybe we'll get to talk a little bit more about that. But like I said, I'm open to alternative models. I'm sure he is as well. That's how science progresses.
I was going to ask you that if you're open to other models outside of your ASC. I don't think I put it in my notes, but I remember thinking about it. That you are open to the idea that there could be other possibilities. Maybe God used a multiple, set of ways. I mean, he's not limited to one. He's not even limited to naturalistic ways, because we're not naturalists. I mean, he could have carried the light here. So you're not opposed to these other ideas. You just saying that from the perspective of the Bible, this seems to be the closest that you can come up with.
Yeah.
All right, and we'll talk about that too.
Sure.
On that. But first, before we do that, I want to get a little bit more into your particular argument. Okay, what is the theory of relativity and what is the conventionality thesis?
So relativity is the branch of physics that was pioneered by Albert Einstein. And he probably wouldn't have called it relativity. He might have called it invariance or something like that. He didn't name it. Other people named it. But the reason it has that name, the reason that name's caught on, is because things that we normally think of as objective and absolute, the same for everybody, like the distance between 2 points. How could people possibly disagree on the distance between 2 points? I mean, we get out our rulers, we measure it. Seems like everybody ought to agree on that. And the rate at which time passes, the amount of time it takes between two events that happen. I mean, if we have a stopwatch, you'd think everybody ought to get the same answer. And when you're all moving at kind of slow speeds and you're all kind of in the same area, you do get pretty much the same answer. But what Einstein discovered is that distances are not objective. They are relative to an observer's motion and potentially position, depending on which synchrony convention you use. So in other words, one person might say the distance between A and B is 100 feet, and another person who's moving at a high speed, maybe half the speed of light, would measure those same two, A and B, and he said, no, it's only 50 feet between A and B. And you're tempted to think, well, which one's right? And Einstein says they're both right, because it turns out that distance is not objective. It is observer dependent, reference frame dependent. Reference frame is how you're moving. And likewise with the amount of time it takes between two events. So let's say you have two lightning strikes, boom, and then another lightning strike over here, boom. And you say, oh, those were 2 seconds apart. Somebody moving at high speed would say, no, they're only 1 second apart. And in fact, somebody moving in a different direction say, no, actually that one happened before that one. We would not even agree on the order of events in some cases. So that's the premise that Einstein developed. And it was to explain a phenomenon that nobody could explain at the time. And that was the fact that the round trip speed of light seems to be observer independent. And that's odd. And just let me illustrate how odd this is. Let's suppose that I'm in a car traveling at 50 miles an hour, and I take a baseball and I throw it out the window, and I can throw a baseball, let's say 50 miles an hour. Somebody on the sidewalk would see that baseball moving at 100 miles an hour. You just add the velocities. But with light, it doesn't work that way. If I'm in a car moving at half the speed of light, and I turn my headlights on, and they're going the speed of light faster than me, you'd think somebody on the sidewalk would see the light from the headlights moving at 1.5 C, but they don't. They see it moving at exactly the speed of light. And so how can it be that the person in the car sees the light moving, the speed of light faster than him, and the person stationary on the sidewalk sees the speed of light moving the speed of light faster than him? It's the same speed. How can that possibly be? And Einstein recognized the answer is because in order to measure a speed, you need to measure a distance and divide by time, right? The speed, you know, the faster something is, the less time it takes to get from A to B. And Einstein realized that if rulers would shrink, if you move faster and faster, if rulers would shrink a little bit, then you'd measure a different distance than somebody who's stationary. And if clocks tick a little bit slower as you're moving faster, then you'd measure a different time. These two effects always combine in such a marvelous way that the speed of light is the same for everybody relative to them. They always think that the speed of light is moving the speed of light faster than them, no matter how they're moving. Even if you speed up, let's say I launch a light beam out and it's moving c faster than me, c representing the speed of light. What if I then accelerate to half the speed of light? You'd think, well, now it's only moving half c relative to me because I'm catching up with it. But no, it would still be c faster than you. It's like it knows what you're doing and then adjusts. It's really strange. And it's because space and time are not the independent things that people assume. So that's really the crux of what's called special relativity. And that's something that Einstein published in 1905. And it works in all situations as long as there's no rotation, as long as the reference frame you're in is not rotating or accelerating, and if there's no gravity. And then to deal with gravity, it took him another 10 years to figure out how to deal with gravity. And so he developed a second theory called the general theory of relativity. And it's all the stuff that's in special, but it also includes gravity and how gravity affects the ticking of clocks, basically the flow of time. Basically, gravity slows the flow of time. And general relativity is very mathematically challenging. And I find it very challenging. Special relativity, I could teach it to a high school student. General relativity, I don't fully grasp the math of it. I've done it. I've done calculations in GR, but it's hard. So that's basically relativity in a nutshell.
All right, and the conventionality thesis, what exactly is that? Is that part of relativity?
Yes. So yeah, let me take it in two steps. The conventionality thesis goes back to what's called the relativity of simultaneity. Basically, in order to measure a speed in one direction, I'd need a clock here and I need a clock over here, right? So I could, one to start, bang, runners on your mark, set, go, boom. And then they run and then they hit the finish line. And then I get the time when they finish and I subtract the two. That's the time it took them to get from A to B. And I take the distance and divide it by the time, and that's the speed. So when you say I'm traveling at 50 miles per hour, that means you can travel a distance of 50 miles in a time of 1 hour. And so if you're faster, you can go a greater distance in a lesser time, et cetera, et cetera. So, but the problem is, in order to measure a one-way speed, the clock at the starting line needs to be synchronized with the clock at the finish line. And one of the things that Einstein discovered is that if one person says, yes, these two clocks are synchronized, another person that's moving relative to him, maybe far away, moving at close to the speed of light, would say, no, those clocks are not synchronized, using the same method. So in other words, if one person says these clocks are both ticking, they're both at noon and so on, they're ticking at exactly the same rate, they're synchronized. A person who's far away might say, no, this clock is 2 seconds ahead of that one. And so it's a little early. Somebody moving in the opposite way would say, actually, no, this clock is ahead of that one. Okay, and so that's called the relativity of simultaneity, the fact that there is no objective synchronization of two clocks. At best, all you can do is you can define synchronization by your own system and say, okay, according to my system, these two clocks are synchronized.
Right.
But you have to leave in mind that somebody else using that same system would say, no, they're not synchronized according to me. Okay, so synchronization is relative to an observer.
So this
so far so good.
I'm sorry. Can you hear me?
Yeah.
Okay. This leads us into what's known as a convention, because you what exactly is a convention? Can you give us examples of that so people understand?
Yeah, it's basically
what is a convention?
Yeah, it's basically a coordinate system, and it comes out of the fact that there is no objective way to synchronize two clocks that everybody will agree on. At best, you can get a group of observers with a common property to agree that those two clocks are synchronized. And so a convention, in this case, it's basically a coordinate system. You know how in maybe in algebra you plotted, x and y. You can plot any position on a graph with x and y. That tells you how far over and how far up. Then later, if you take more advanced algebra, you might learn polar coordinates, where you have r, distance out, and then theta. And you can measure the same. You can use either system to plot a point on a graph and plot the same points using either x and y or r and theta. Those are two different coordinate systems. They're conventions. And it's the same way with stuff in space, except we have x, y, and z. We can go up and down now. Okay, so in and out, up and down, and t, time. So if I were to tell you, okay, let's have a Bible study later, I would need to give you, let's meet in person and have a Bible study. I would need to give you 4 pieces of information: X, Y, Z, and the time. And that would tell you, right? So X, Y, and Z, X and Y might be, well, at the intersection of this street and that street, that's where I live. And Z would be, I'm on the 3rd floor, and let's meet at 8 o'clock. That's the time, T. Okay. And there's different ways of doing that. And so that's really what ASC is, the Anisotropic Synchrony Convention. It's a system of marking X, Y, Z, and T. And it's identical to the system Einstein used for X, Y, and Z, but T is different. And so basically it's a way of marking time. And one of the things that Einstein did was he said, okay, given that we can't objectively synchronize two clocks to where everybody will agree, maybe we can get a group of people to agree. And so he developed what's called the Einstein Synchrony Convention, or Isotropic Synchrony Convention. He said, we know the round trip speed of light. Let's assume that from my perspective, light goes the same speed that way as it does this way. And if you did that, you could synchronize two clocks by sending a light beam out and then reflecting it back. And let's say the total time takes 2 seconds, right? I send the light out to a mirror, bounce it back, and the whole thing took 2 seconds. Einstein said, let's assume that it took 1 second to get there and 1 second to get back. Then you could set that other clock over by the mirror to be 1 second ahead of the time sent by this one, and then they would be synchronized. Now, Einstein agrees that's just a convention because somebody else who's moving relative to them would not agree that those clocks are synchronized. And Einstein also pointed out that you don't have to have the speed of light be the same in this direction as that direction. You could have it take all 2 seconds to get there and no time to come back. You can have it take no time to get there and 2 seconds to get back. And people say, why would it be different? But they're missing the point. It's not a question of what's light doing. Light just does what it does. It doesn't know anything. It's just a question of how we synchronize clocks. And there's no way to do it that everybody in the universe will agree. So what Einstein did and what most physicists do today is they'll assume that the speed of light is the same that way as this way. And that tells them how to define clocks, like how to define what constitutes synchronized clocks. Basically, they're reading the same time at the same time. But you don't have to do it that way. And Einstein pointed that out, that you could do it another way. So anisotropic synchrony convention is a way of synchronizing clocks where light, when it's going outward, moves at 1/2 c. And when it's moving toward an observer, it's instant. It takes no time at all. And right. You can do that, and all the physics works that way. And basically, my argument is that's what the Bible's using when it marks events, because that convention was used by all ancient societies. It still makes sense today. The other convention is useful when you want to do physics problems because the math's easier.
All right. I don't want to move too far ahead. You're getting further ahead than I am right at the moment. I do want to ask a few things about that on the convention. Well, a passage of Einstein out of his primer book on relativity that you often cite is a passage where he says that that the speed, referencing the speed of light, it's not a supposition nor a hypothesis about the physical nature of light, but a stipulation of which I choose of my own free will. So yes. The object of it is that okay, and this is something that confuses a lot of people, because a lot of people will attack it like you're saying something against the nature of light, or the universe is just not that way, and you're not actually attacking natural laws. You're not saying that the round trip speed of light's different. In fact,
Right.
you've actually said the opposite. You accept that the round trip speed of light will always equal out c. But you're arguing exactly what Einstein argued, that it is a stipulation. It's a way which we synchronize those two clocks. Correct?
Yeah. Einstein recognized that the one-way speed of light is not a property of nature, as you pointed out. It's a stipulation. It's not a hypothesis, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. How do we decide that these two clocks are really synchronized? I pick a one-way speed of light, and that tells me whether or not they're synchronized. That's how you do it. And Einstein chose. He usually chose to make it the same speed in both directions. That's why we call it the Einstein synchrony convention, because if you do it that way, the math is easier. But it's a mathematical shortcut. But there's no objective. It's not like the Einstein synchrony convention and is more objectively true than the ASC synchrony convention. They're both conventions. They're both like coordinate systems, like polar coordinates versus x and y, rectangular coordinates. So it's just a question of which one is more convenient for the situation.
And you would say that in relativity, from what I understand, both systems are considered valid, or both conventions are considered valid.
Oh yes, yep, no doubt.
Let's get into the one-way speed of light. This is probably going to be more of the more interesting thing, because people have tried to measure the one-way speed of light, and there's all kinds of issues involved with one-way speed of light. But first, okay, I guess I got two questions on this. First, define what exactly is the one-way speed of light, especially relative to the round-trip speed of light, and two, what is the issues involved on trying to measure the one-way speed of light?
Okay, so the round-trip speed, that's easy. That's where we take a beam of light, send it out, bounce it off a mirror, bring it back, and you'll find that if the distance between you and the mirror, the source and the mirror, is constant, the time will always be constant. So the round-trip speed of light is the total distance it travels divided by the total time, and that is always, in vacuum, it is always 186,282.397 miles per second, and nothing changes that, or 2.9979 times 10 to the 8th meters per second. Nothing changes that. But what's the one-way speed? That would be the speed it travels from A to B, but not back. And that will depend on whether or not the clocks at A and B are synchronized. Let's suppose that I send out my pulse at noon, and it arrives at the other clock at 12:05, but that other clock is 5 minutes fast. So did it really take 5 minutes? Normally you'd subtract the time. You'd say 12:05 minus 12. That would be 5 minutes or whatever it is. And but it didn't really take 5 minutes to get there. It's just that those clocks were not synchronized. So one-way speeds will depend necessarily on how you on how you define what constitutes synchronized clocks. And if you synchronize clocks using light under the assumption that the speed that way is the same as that way, and then you measure the one-way speed, you'll find it is the same that way as that way. But that's what you assumed at the start. If you use the speed of light being instantaneous when it's toward me and half c when it's away, and use that to synchronize your clocks, and then measure the speed of light using those clocks, you'll find that indeed the speed of light is half c that way and infinite when it's toward me. Okay, so that's the issue there. Any experiment to measure the one-way speed of light would have to involve two clocks that are separated by distance and are synchronized. And the problem is, according to Einstein, there is no objective way to synchronize two clocks. And so there will always be some leeway in how one-way speeds are defined. Now, the slower the speed, the less important that is. And so if you're driving down at 55 miles per hour or let's say you're driving 80 miles per hour in a 65 mile per hour zone, and the cop pulls you over, you can't say, hey, you can't objectively know my one-way speed. That's not going to work, because cars are so slow compared to the speed of light that the leeway gets smaller the slower the speed is. But for the speed of light, the leeway is anything between half c and infinite. So the speed can actually be infinite in one direction.
It's also important. It's also important to understand that you're talking about directly toward an observer. So you're not talking
Yes.
about at an angle or anything like that. And we'll get into that a little bit because that's one of the objections that people sometimes raise up. And I'll get to that in here in a little bit. But as far as the slowness thing, I think this is one of the arguments that you mentioned in your book, Physics of Einstein. Some people say, well, what if we move the clocks slowly? And so how would you respond to that if someone says, okay, we just move it just a little bit slowly?
Yep. It's been tried. And by the way, everything that laymen have come up to me and said, what about this? It's been tried. There have been scientists that have proposed that in the literature. So that this particular method is called slow clock transport. We know that motion affects the passage of time, right? So moving a clock causes it to tick at a different rate. And so the very act of moving a clock causes it to become desynchronized. But the slower you move the clock, the less that effect is. And so the idea is if you move it as slowly as possible from A to B, they'll still be synchronized. And it is true that in the limit, as the speed goes to zero, if you move a clock, if you take two clocks that are synchronized and you move one out here as slowly as possible, and then you move it back as slowly as possible, they will still be synchronized. That is true. But how do you know the clock didn't gain a minute when you moved it out and then lost a minute when you moved it back? So they'd still be synchronized, but when they're separated, they're not synchronized. And it turns out that if you look at the time dilation formula, the full, what's called the epsilon time dilation formula developed by John Money back in the 70s, that's exactly what happens. If the speed of light's different in different directions, then the rate at which clocks tick, time dilation, is different that way than it is this way. And so sure enough, a clock can gain a minute going out and then it can lose a minute coming back. So they're still synchronized, but the assumption that they were synchronized when they were separated would be false. So that's the problem with slow clock transport. Is it fails to include the effect of time dilation, and the effect of time dilation in the full formula depends on the one-way speed of light. So you'd have to already know the one-way speed of light to know if your clocks are synchronized.
That's something I was going to ask you about, because you mentioned this several times in your book, that a lot of the experiments that are being done has to assume the one-way speed of light ahead of time, or they assume the ESC convention in the process. And some of the responses that I heard on the internet, like I don't know if you ever heard of a girl named Maddie. She got like a Science Side Up, I think it's her channel, YouTube channel. But anyway, she claims she worked in the scientific area. She says she's not relativity is not her area of expertise, but I don't know why she was talking on it or trying to respond to you, but anyway, but she said that wasn't her area of expertise. She also said biblical studies and literary genre wasn't her area of expertise, but she made assertions about Genesis being poetic. So, but anyway, I was watching the video yesterday on that, where she was making arguments, and I noticed some of the arguments actually assumed the ESC, where she said, well, then why is it the same as there back here? I mean, she basically assumed the ESC when she was trying to argue against the ASC.
Yep.
And that's begging the question, correct?
That's right. Yep. And every experiment, basically every experiment that attempts to measure the one-way speed of light objectively, they always assume a synchrony convention at the outset, usually the Einstein synchrony convention, but they don't realize they're doing it. They don't realize they're doing it. They assume that something's the same that way or is that way. That subtly depends on the speed of light. Even very educated physicists throughout the 20th century debated this issue. And some of them thought they came up with an experiment to measure the one-way speed of light. And then in the next issue of the same journal, there'd be somebody refuting it, pointing out that they assumed a synchrony convention. One example, I thought it was clever. Some guy says, let's take two physical clocks, analog clocks. They got the hour hand and the minute hand, and we'll take a long rod and we'll connect the hour hand of this clock to the hour hand or the minute hand or the second hand, whatever, so that they're in that way they have to be exactly synchronized. But that actually assumes a synchrony convention, because that assumes that rod is infinitely rigid, such that when this clock moves, the other one, the rod instantaneously moves at the other end, but it doesn't. When you push on this end of a rod, it takes a little bit of time for the other end to move. Now, it's fast, but it turns out it's the speed of sound in the material is how fast. When you push on this end of a rod, it takes a small amount of time for the other end to move. And so the two clocks would not be exactly synchronized by that method. And the next paper then pointed that out, that won't work. So that's one example. Basically, every method to try and measure the one-way speed of light will either assume slow clock transport, or it will use a synchronizing mechanism that assumes the one-way speed of light. And both of those beg the question because they're circular.
It was actually something you mentioned in your book that it might be the experiment you were talking about, but you mentioned this experiment that in your book that was actually peer review. It was in peer review, but I think you might have said it was a friend of yours. But but in the experiment, it actually assumed the ESV or ESE in reference to the round trip speed of light, one way or something like that. But he did publish in peer review. He was one of the that published in peer review, and that you mentioned in your book, Physics of Einstein. Do you want to explain that, or?
Yeah, my friend Ron Samek published that, and it was just a little paragraph in a paper that was about his measurements of binary stars, and his work is exceptional. He's a fine astronomer, but I do believe he was mistaken in that paragraph where he says, "Well, this refutes the one-way speed of light being infinite." Because basically, what he was doing is a variation of the first measurement of the speed of light, which was done by an astronomer named Romer. And some people will think, doesn't Hal know that the first measurement of the speed of light was a one-way trip even before it was fleshed out? Basically, what Romer did and what Ron was doing was similar to that. Was Romer said that he's using the moons of Jupiter as a clock, because the moons of Jupiter have a very precise orbit, especially Io, which is Io, which is the innermost of Jupiter's moons. And when they first peek out from Jupiter, you can measure that time very precisely. And he noticed that when the Earth is on one side of the sun that's on the same side as Jupiter, these little transits are a little bit early. And when the Earth's on or near the other side of the sun, the trips are a little bit late. And he assumed that was due to the fact that the light had to travel an extra distance to get to the Earth. Okay, so he's assuming that that's the reason for why the trips are late or early, is because the light's taking a little extra time to travel that extra distance, which would mean he's measuring the one-way speed of light. But it really doesn't, because what he failed to include was time dilation. And he could certainly be forgiven for that, because Einstein hadn't been around to discover time dilation yet. But Romer didn't know about it. And had he known about that, he would have recognized that the fact that the Earth orbits the sun causes the clock to tick at a slightly different rate when it's moving toward Jupiter as when it's moving away from Jupiter, if you're using the anisotropic synchrony convention. Now, he didn't know that. And so he thought he was measuring a one-way speed of light, but he was actually just measuring a round-trip speed of light, because he's assuming that he basically disregarded time dilation. And time dilation can only be neglected for slow speeds if you're using the Einstein synchrony convention. If you're using anisotropic, then even at slow speeds, you have to include it.
So you would define anisotropic synchrony convention as light, reference to us as the observer, directly when the light's directed toward us directly, that it's instantaneously, but it's half c when it goes back. Is that correct? All right. And so
right. And there's an equation that gives the intermediate directions as well.
Right. And so every now and then you'll hear somebody saying that they can falsify that, and then that seems kind of absurd, the idea of falsifying a convention. Right. I know sometimes you will hear people say that. So what do you think of that?
Mm-hmm. Yeah, so basically the way we synchronize clocks will determine what result we get for when we measure a one-way speed. And to say, well, you can't synchronize clocks that way. Well, yes, I can. It's a convention. And so when anybody says, well, we can prove the Einstein synchrony convention is true, or the anisotropic is false, or vice versa, I've had people say, we think your convention's the true one. I said, then you don't get it, because I'm not arguing that one is more true than the other. They're just different. It's kind of like if somebody said, this table is 1 yard long, and somebody said, no, it's not, it's 3 feet long. And somebody says, I can devise an experiment to find whether it's really 3 feet long or whether it's 1 yard long, I'm going to say you don't understand units of measurement, because 3 feet and 1 yard are the same thing. Okay. And so likewise, when we measure events in space and we say that happened 1,000 years ago by the Einstein synchrony convention, but it happened right now by the anisotropic synchrony convention, we're not actually talking about a difference of fact. We're talking about a difference of how we choose to mark time, and that will affect the one-way speed of light, or vice versa. You choose the one-way speed of light, that'll affect how you define what means now at a distance. And there's no objective way to do it because of the nature of the universe that Einstein described. And so really the Einstein synchrony convention and the anisotropic synchrony convention are simply 2 different coordinate systems by which we mark the X, Y, Z, and T of any event in the universe. And they will differ on the T coordinate because we're using a different synchrony convention.
Right. And you would, okay, if I think this is a correct understanding of your position, you would say the issue is not if ASC is better or worse or more accurate than ESC. The issue is which synchrony convention does the Bible use is the issue.
Yes.
Is that correct?
Exactly. Yeah. That's it.
Okay. And so that's, I want to talk just for a few minutes about that, because you kind of hinted at it earlier, but you said that the ancient world, basically, to the ancient world, if they see it happening right now, then it's happening right now. Is that correct?
Yeah. So they're tacitly using the anisotropic synchrony convention, and that makes perfect sense, right? I mean, if you see a deer on a distant hill over there and you're watching it graze, you don't think to yourself, wow, I'm looking at that deer now, but I wonder how many millions of years ago that deer really did that. I mean, it doesn't occur to you to think that way. It's very natural for us to take what we see now as happening now. And under the anisotropic synchrony convention, that's how we choose to synchronize clocks. And therefore the light, when it's moving toward me, is instantaneous. And so what I see happening now actually is happening now. It's a very natural way to do it. And all ancient cultures had to do that because they didn't know what the round trip speed of light was. So they didn't think to subtract it off from when they see an event happen. They didn't think, well, that really happened a long time ago. They thought, well, it's happening now. And I think the Bible uses that language. It's perfectly legitimate even today. It's just because the Bible was designed to communicate, not just to 21st century physicists, but to everybody. And, it's going to use the ancient convention, a convention that would have been understood by everybody and is still understood today, rather than a convention that wouldn't be invented until the 20th century.
One of the arguments that Maddie makes on Science It Up on that video that I watched, she tried to say, well, because she was responding to your video where you talked to this guy from Origins, I think it's called, and you were talking about distant starlight. And I've actually seen the video myself. I didn't watch it prepping for this one because I've already seen that video all the way through. But she was responding to that, and she said that that it's not wrong to use modern understanding of it in ancient, but I think she misrepresent what you were actually arguing for. What you're talking about is more exegetical. The object, again, is not if ASC and ESC are better than the other. The object is what the Bible used. If you try to take modern a convention that's used, like say by most astronomers today, and you import that back into the scriptures when they're not using that convention, then that's a word study fallacy called semantic anachronism fallacy, correct?
That's right. You got it.
So the issue, as you put it in your book, is an exegetical one, not one of which convention is correct.
Right. And I'm not suggesting that, the Bible is providing all the details on the anisotropic synchrony convention that I am. I'm not suggesting that. But I do think, because all ancient cultures would define now for something that's happening out in space, if they see it now, they would define that as happening now. That's a very natural way to think about things. The Bible seems to use that language as well. So, some people say, well, the Bible's not using any synchrony conventions. Well, no, it has to, because it talks about events happening in time and in space. And therefore, it has to assume a synchrony convention. It's either going to assume one that would have been understood by all cultures at all times, or one that would only be understood in the 21st century. And that position casts into doubt the principle of the perspicuity of Scripture, the idea that the Scriptures are fundamentally clear and are meant to be understood. See, if God were to use a convention in Scripture that would not be understood until thousands of years later, then how do we know we understand it now? How do we know that God isn't using language that won't be understood for another 1,000 years? And then it calls into question everything that the Scriptures teach. They have to be speaking to the original audience. And so we have to get our minds in that set. I think that's important.
One of the biblical proof texts you often use is Genesis 1:14 through 1:16, when God created the stars. And then in verse, I believe it's verse 16, God said, and it was so, which suggests it's immediate fulfillment. So in other words, it's not saying,
yeah, in verse 15.
Yeah, go ahead.
So Genesis 1:14, then God said, let there be lights in the expanse of the heavens to separate the day from the night, and let them be for signs and for seasons and for days and years. And then we find out later what those, he gives more details on what those are. The greater light, the sun; the lesser light, the moon; the stars also. So these lights, and what's their purpose? Verse 15, and let them be for lights in the expanse of the heavens to give light on the earth. So the purpose is to give light on the earth. And it says, and it was so. What was so? Well, he made the stars, he made the luminaries, and they gave light on the earth. So I believe they immediately fulfilled their God-ordained rule of giving light on the earth. It didn't take time for Alpha Centauri to blink. Adam didn't have to wait 4.3 years for Alpha Centauri to blink on and then the other stars to blink on. Apparently, they immediately gave their light on the earth. And that would imply that the Bible's using, when it talks about the creation of the stars on day 4 and their light reaching earth apparently immediately, it's using an anisotropic synchrony convention.
All right. I've got a I'm sorry.
I've got a series of objections that people have raised on the internet. Now, I think you've stated several times, including in your book, that a lot of times, and you said it also in your response to Peter on your Biblical Science Institute website, which I will be linking in the description box below. But you've said that several times that sometimes people will publish things on the internet that clearly it will never make it into peer review because of some of the claims that they make and so forth. Okay, and I've got some common ones that some people raised up, and so these would be interesting to go over real quick. The first one I got, there was a supernova that blew up, and it sent images around, I guess, due to gravitational lensing, which I'm sure you're going to explain that in a minute. But and so we got several different images, but one of the images appeared a year later. So some people throw this out there, and I think you, Ross, threw it out there in your debate with him on Revealed Apologetics as well, and try to claim that this disproves the idea of the one-way speed light being instantaneous. Now, of course, your argument is it's instantaneous toward us, but I'm sure you're going to explain that in a minute. But so what's the deal here?
Yeah, it's the critic here has committed the formal fallacy of affirming the consequent. That's where he says, if the Einstein synchrony convention is true, and already we got a red flag, because it's not a question of whether or not it's true, it's just a question of which one you want to use. They're equally legitimate conventions. But he's arguing that the Einstein synchrony convention is true because it predicts that the light from all these should take a different amounts of time. But what he failed to consider is that the anisotropic synchrony convention also makes that prediction. They make exactly the same prediction. So what's happening here is there's a distant galaxy, and one star in that galaxy blows up. And when a star blows up, it's as bright as all the rest of the stars in the galaxy. It's extremely bright. And the light from that galaxy started moving sort of toward Earth in kind of general direction. And then there was a galaxy cluster in between that star and the Earth. And so the light actually went around the galaxy and got bent by the gravity of all those stars in that galaxy cluster. And some of that light got focused to Earth, and it formed actually 4 different images of the same star, and they all arrived at about the same time. Then a 5th image, which had taken a longer path because it got bent more, because it's just the shape of the cluster of galaxies. It arrived about a year later. And so we got to see a 5th image a year later. And so people say, well, obviously that means the speed of light toward us is finite because this one took a longer path, and sure enough, it took longer to get there. But what they failed to recognize is in the anisotropic synchrony convention, light is only instant if it's exactly toward you. If it's a little bit off, the speed will be finite. And I put the equation in my original paper on this so they can calculate the speed, you know. So on that first leg of the journey, the light is not aimed directly at the Earth. It's just sort of toward the Earth. So it'll be faster than C, but it won't be instant. And then once it gets bent around the galaxies, then it'll speed up. And once it's directly toward the Earth, then it takes no time. But that other light path took a longer, it was aimed further away from the Earth. And so it will be slower than the first 4 beams. And so sure enough, you go through the math, it'll arrive 1 year later, according to the anisotropic synchrony convention or the Einstein synchrony convention. And by the way, that's true of any experiment. If you do the math properly, you have to get exactly the same answer on what we observe on Earth, because after all, we're talking about 2 coordinate systems, not 2 different versions of reality, but rather 2 different descriptions of the same reality.
On the response to Peter on your website in Biblical Science Institute, you actually have this diagram where you actually show it and go through it using letter variables to identify the different light rays and showing how the ASC is consistent with this information. And I think that's very helpful. So I will be including a link to that article in the description box below, because you really go in depth into explaining all that. And I think that's very helpful. All right. Now my next, say again.
Yeah, I said pictures help. So please, yeah, the viewers, please read that article and take a look at the graph. You'll see what I mean. The angle is larger for the one that takes longer, just as ASC predicts.
This next one is also a common objection. This is some people raise up Maxwell's equation on the physical nature of light. They say that disproves ASC lacks a see, what is it? I can't hardly read it. Physical. But anyway, they're claiming that his arguments on gravitational and field or something like that would disprove it. I found a biologos argument or a biologos article where they try to set them respond. I don't know if you've responded to biologos article or not. It's on responding to you on the Distant Starlight. They give a series of articles. A lot of it's nonsense, but they raise up some common objections that sometimes gets raised up. And in a little bit, I'm gonna probably share my screen and we'll go to that article and look at a thought experiment that they're doing. Because I remember you mentioning that sometimes people do these thought experiments because they think they are able to falsify that. And Biologos had one particular one. But in any given case, what is this deal with Maxwell's equations, and why do people think that it disproves the ASC?
Okay, so Maxwell's equations are 4 equations that were either developed by James Clerk Maxwell, who's a creationist, by the way. And but what they do is they relate energy, they relate, electric fields and magnetic fields. They express the relationship between those 2. And they are incredibly powerful because you can any kind of problem you can think of in terms of solving for an electric field or magnetic field, you would use Maxwell's equations to do it, or things that have been developed as a result of those equations. And there are 2 different forms of Maxwell's equations, and you have to be pretty knowledgeable of mathematics to understand how they work, because you have to, there's the differential form, which we'll use del's, which is like a derivative in 3 dimensions. And then there's the integral form. And if you look at the integral form, you'll find these little circles on the integral sign. And what those mean is that you've integrated around a round trip. And so it's like a closed path, like a surface, like the entire surface of a circle. Or if you're making a circle, you come back to the starting point. And so the integral forms of all those show that they are only dealing with round trip phenomena. So if it's inexcusable to look at the integral form and say, well, this proves the one-way speed of light. It doesn't. See, one of the things that you find, though, usually when using the differential form, is if you solve these equations, you find that a vibrating magnetic field will produce a vibrating electric field, which will produce a vibrating magnetic field, and so on. And that's what light is. It's a propagating electromagnetic wave. And those equations also predict the speed of that electromagnetic wave. And it turns out to be, lo and behold, the speed of light. And Maxwell knew that, and he realized, oh, light must be an electromagnetic phenomenon, which it is. Brilliant. But most people assume that it's finding the one-way speed of light. But if you look at the integral forms, no, it's a round trip speed, because they're all closed integrals. What about the differential form? A guy named Carlo Giannani demonstrated back in, I think, 1980, that the differential forms that are normally used assume the Einstein synchrony convention. And if you don't assume, and he derived the generic version of Maxwell's field equations without synchrony dependence. And if you go through the math, lo and behold, you can get light traveling at different speed that way than that way. So Maxwell's equations do not, repeat, they do not demonstrate the one-way speed of light. They do demonstrate that the round trip speed of light in vacuum has to be c, but they leave open the one-way speed of light. And again, that was demonstrated conclusively by Carlo Giannani back, I think, in 1980. But if you look into his work, you can go through all the gory detail. And the math is difficult, but it works. It works.
Right.
So Maxwell's equations are consistent with ASC.
Right. I'm going to go ahead and share my screen real quick. All right. Can you see my screen?
It's coming. Okay. Yes.
All right. Take that out. All right. All right. By the way, this is Dr. Jason Lyle's peer review article. It's on Answers Research Journal. It's free, so I will suggest reading that. It is really good. I read it all the way through. But this right here is the article by BioLogos responding to Dr. Jason Lyle. And they try to come up with some, like I said, a few common ones and then some not so common ones. But they have a railroad analogy, a thought experiment. I want to pass this by you, Dr. Lyle, and see how you respond to this. All right. They said, to understand what went wrong here, suppose that the local railroad company wants to boast that it operates at traveling speeds that are virtually infinite into the city. However, their trains suffer from physical limitations and have a maximum speed of about 50 miles per hour. To overcome this quandary, the railroad company decides to change the synchronization convention of the clocks in all of its stations. The clocks are synchronized in such a way that trains into the city seem to arrive instantaneously, while trains out of the city travel at half the speed, say 25 miles per hour. With such amazing advancements, it does not take long before somebody starts a lawsuit against the company, especially since we are talking about the U.S. here. In its own defense, the company might say that the way of synchronizing clocks is technically allowed, just like the standard convention. It kind of reminds me of what you said about the speed of cars. The judge is taken somewhat off guard by this unusual proposal and decides to consult with expert physicists on the issue. Their advice entails that the accuracy of the advertised claim should be determined using synchronization, which is truthful of the physical limitations of trains, i.e. the standard convention. The judge decides to follow this piece of advice, and the railroad company loses the lawsuit. Of course, our example is subject to simplification. For example, in ASC, every station, they put in quotes, has its own synchronization such that the speed is infinite towards every observer, which I can already see a problem there, or regardless of his or her location. Also, for light waves, the physical limitations are derived from Maxwell's theory. While those of trains are measured directly, these differences do not change the point of our analogy that physical limitations should be taken into account when discussing speeds. What do you think of their... Let me get this off of the share screen here. All right. What do you think of that analogy, the railroad analogy? It sounds similar to what you said about the cars traveling at 55 miles an hour wouldn't affect it much. Do you think that this is a good representation of your argument? Do you? I think they're almost arguing that you can't use synchronized clocks in that way. Is what it sounds like.
Well, I think the person who wrote the article doesn't really have a good grasp of the physics of Einstein, because that is what I would call that an example of a false analogy, because the speed of light is very different from the speed of trains, for example. And you could technically synchronize clocks according to that convention that they're using. But And you'd say, well, the train effectively is traveling instantaneously one way. But the problem is there are things that are faster than trains. And if you use that synchrony convention, you would have anything that's faster than train arriving at its destination before it left. Okay. And so you would have a problem with causality. And so you could technically use that synchrony convention, but it would be one that is inconsistent with cause and effect. Whereas the anisotropic synchrony convention, because nothing is faster than light, is consistent with cause and effect. And so that's why I think that's a false analogy. Also, passengers on the train would experience time as they moved from the source to the destination. And that's a difference as well. Light does not experience time. From light's point of view, every trip is instantaneous, no matter what convention you use. And so there are two things that make that an example of a false analogy. Two real quick examples right there. And then a third would be, when you really understand the physics of Einstein, you need to understand that simultaneity, there's a principle called the simultaneity of relativity, or pardon me, the relativity of simultaneity. The fact that there's no objective way to synchronize two clocks, but you can approximately synchronize them. And that would disallow the claim that something like a train can travel instantaneously.
All right. I have this one comes up a lot. Sometimes I hear it like distant galaxies don't look like galaxies close up, and sometimes I heard that nearby galaxies don't look like galaxies close up. Sometimes they commit the reification fallacy, like galaxies far away look old, and compared to the ones near us. And so, how do you respond to that when people think that? Well, for one thing, the galaxies don't look old or young, I think is what you put in your book. They look the way they look. So they're assuming the reification fallacy in the process.
The funny thing is, people who claim that, well, yeah, distant galaxies, they look very different from nearby galaxies. I would say not according to the James Webb Space Telescope, because all those people who used to believe that, because when Hubble looked at these most distant galaxies, they did look a little bit different. But that's because the light had been redshifted to the point you're seeing different frequencies. You look at it in James Webb, and it's like, that looks pretty much the same as nearby galaxies. And so, in fact, one of the technical papers I looked at when I wrote my write-up on the observations of the James Webb Space Telescope, he says, we're going to have to rethink galaxy evolution, because these galaxies are already mature. They're already spiral galaxies. They're massive. They're not clumpy like we were expecting them to be. So everything I'm seeing with the James Webb Space Telescope and its data shows that distant galaxies are very similar to nearby galaxies in terms of their morphology, in terms of their chemistry. That's something that the secularists were astonished at. I predicted it. I predicted that the most distant galaxies would have roughly the same, well, I won't say the same, but they would have heavier elements in them as nearby galaxies do. Whereas the secularists were predicting that the farthest galaxies, in their view, the earliest galaxies, shouldn't have the heavy elements, because those are produced allegedly in stars. The Big Bang can't make them. And so therefore the earliest galaxies shouldn't have them. Well, we now know that's wrong. The earliest galaxies do have heavy elements in them, and James Webb is equipped with a spectrograph that can detect the presence of heavy elements by their spectral signature. So it's not true. Distant galaxies look pretty similar to nearby galaxies.
Yeah. And in your peer-reviewed journal article, you actually talked about the spiral rings and so forth are winding themselves down, and we talked about that in our last video together. Another one that comes up a lot, it comes up in the biologos argument. It's also, I think, came up in your in the thing that Peter said in your response to Peter, where he's actually mentioned it. Some people argue that if the ASC model was true, then the galaxies would shift toward the blue shift instead of redshift it, or something like that. Could you explain that and why that doesn't work when they talk about the light spectrum and that sort of thing? I think you gave a kind of a funny analogy when you responded to Peter about water as well, like you would be able to shift toward infrared or something like that.
Right, I remember that now. Yeah. So light, like I mentioned earlier, light, when it passes through a substance like water, its speed will drop. And in water, it drops to about 75%. the speed of light in vacuum. So it drops down to 0.75 C. In a diamond, it's around half, 0.5 C. So it really slows down in a diamond. And so Peter was arguing that if the anisotropic synchrony convention were, or the model, I forget if he's referring to the convention or the model, but in any case, he's saying that the light would be very blue shifted, but it wouldn't be, because synchrony conventions don't affect the frequency of light. So the frequency is how many peaks travel through a plane. So imagine a wave, okay? And imagine that wave's moving. And so you got a peak, trough, and every second you get so many peaks that move past a plane. Peak, 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 peak as it moves past. The anisotropic synchrony convention will give a different measurement for the wavelength of the light because the speed's different, but the frequency is totally unaffected. And I pointed out that if changing the speed of light changed the frequency, then when you're in water, everything ought to look, I guess it would look redshifted because the speed of light is reduced in water. But in fact, it doesn't. The colors don't change when you're underwater. There's that little, I mean, because you have complete internal reflection, a lot of times you can't see, but there's a little, if you've ever been underwater, there's a little place above you where you can see outside. And of course, the light's refracted, but the colors look the same. So the speed of light, using a different speed of light because you're using a different synchrony convention has no effect on the frequency, which is what we think of in terms of color.
All right. The next objection, why do we? Well, I've got one here, but I think I would have to go to the biologos argument because I think it's in the biologos argument. It says, "What about light echoes?" I don't know if you understand that one or not. They mentioned something about light echoes. So can you explain that?
So this is another place where they. Yeah, there's another place where they have mischaracterized the anisotropic synchrony convention. They're not representing it accurately, so it's a strawman fallacy. But there are places in space where stars have given off. There's gas surrounding stars, maybe gas that they've ejected in space, and then the star explodes, and it of course the light that it releases during this explosion is enormous, and sometimes the light, some of that light we see directly. It comes toward the Earth, and we see the star when it's supernovas. But then decades later, if you point a telescope there, you'll see light that has gone out to the side and then reflected off and then toward the Earth, okay? And that's called a light echo, and it gets bigger every year because the light takes time to travel from the star out to the gas where it's then reflected toward the Earth. And people say, see, that shows the speed of light is not infinite. Well, I agree. It's not infinite in that direction. The anisotropic synchrony convention only has the speed of light infinite when it's directly toward the observer. If it's perpendicular to the observer, and these light echoes are roughly perpendicular, then the speed of light is c. It's the same as the round trip speed, right? And in fact, I gave the equation in my paper that shows the speed of light for different angles. And if you plug in 90 degrees into that, lo and behold, you'll find that the speed of light, the one-way speed of light, is c when it's perpendicular to your line of sight. That's why it's half c when it's away from you, and infinite one toward you.
Right. That's why I emphasized it earlier, because that's important to understand that it's instantaneous when it's toward the observer. There's another one that comes up. Why do we see a Doppler effect? I'm assuming this is because distant galaxies redshifted. If the light is instantaneous, this might be on the biologos website as well, or the article as well. That seems to me to assume the ESC. Is that correct? Do you think he's assuming the ESC when they say that?
Yes, but he doesn't realize he's doing it because so here's the argument. Redshift, you have light, let's say, that's moving toward me from an object that's moving away from me. Okay, and so as he moves away, the next peak of light will be a little bit further away. And so that the wavelength of that light will be increased if the speed of light's finite. But if the speed of light's instant, you'd say, well, why would you have a redshift? Because the light takes no time to get from there to here. And the answer is time dilation. The formula for time dilation includes the one-way speed of light. Normally it's suppressed in the expression that Einstein uses for time dilation, because he's assuming the Einstein synchrony convention. And when you assume the Einstein synchrony convention, the formula for time dilation gets a little easier, and it's only got a quadratic dependence, which means for slow moving things, it's basically negligible. But for the anisotropic synchrony convention, the time dilation formula is different. And so something that's moving away will be redshifted because the time has slowed down on that object. And so instead of releasing a peak of light every boom, 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 it's slower. So it's going to go boom, boom, boom. And when you have slower frequency, that means the light will be redshifted. And so, if you do the math, the Doppler shift is identical between the anisotropic convention and the Einstein synchrony convention.
You say that both
and it would have to be.
So you would say both conventions predict the same thing. In other words,
yes, but the exact mechanism is different, and that's what's interesting, because in the Einstein synchrony convention, for slow moving objects that are moving away, the redshift is almost entirely due not to time dilation, but due to the fact that the object is at a greater distance when it emits the next peak, and therefore it takes a little longer for the next peak to get to Earth, and that's where it causes the redshift. In the anisotropic synchrony convention, the light takes no time to get from the object to the Earth, but the time dilation is greater for an object that's receding from the Earth. And so the reason the light's redshifted is because the clocks are ticking slower, effectively. And so you get exactly the same observed result, but the qualitative effect as to what's producing it is different between the two conventions. And there's no way to observationally distinguish between the two because they are, after all, coordinate systems.
Right. And that's why that they assume the ESC. They just assume that the reason we see the redshift is therefore because it's getting further away. But we would also expect that in
the light's taking increasing time.
Yeah.
Mm-hmm.
All right.
But the fact is, if you run through if you'd run through the formula for time dilation, which I've included in the book, The Physics of Einstein, I included the formula for time dilation under ASC. If you run through that formula, you'll find that the time is dilated and you get exactly the same redshift, whether you use ASC or ESC.
Right. Would you say the ASC, this is an objection that's very common, I heard. I don't know if this deals with the Maxwell thing or not, but a lot of people will say that they think that gravitational that it would create a ASC, if it was instantaneous toward us, it would create a massive gravitational field. I know you actually responded to the gravitational field argument in your book, Physics of Einstein. Do you want to explain that one real quick?
Yeah, I believe the error is due to the fallacy of affirming the consequent again. So one of the ways in which you can get light to move at an apparently different speed as seen from a faraway observer is an enormous gravitational well. And so people are assuming because a gravitational well will change the speed of light, therefore any change in the one-way speed of light is caused by a gravitational well. That doesn't follow logically. And so the fact is the one-way speed of light can be anything you like because it's a matter of how you choose to synchronize clocks separated by distance. And keep in mind, what we're dealing with here is a coordinate system. The anisotropic synchrony convention and the Einstein synchrony convention are two coordinate systems that describe the same underlying reality. Now, to say that switching to a different coordinate system would cause a gravitational well is absurd. I mean, imagine I'm plotting, I'm doing a high school math problem. I'm plotting X and Y, and then I decide to plot the same thing using polar coordinates, where I'm using r and theta to describe the same plot. Would that create like a black hole? Would that create gravity because I'm using a different coordinate system? Of course not. So the way we choose to mark X, Y, Z, and T, our convention for describing what happens in space and when, does not have any effect on the actual universe. It can't create gravity. It's not something that requires gravity to create it. It's just a coordinate system.
All right, I'm going to share my screen again real quick. I'm going to see what you think of this particular argument. It's again from the Biologos argument article. All right, do you see it?
It's coming. Hold on.
Okay. I think it's below this.
Oops. There it comes. Yeah.
All right, right here. They're claiming that this would revive the geocentric argument. It says, I can imagine that this leaves you with more questions than answers regarding the ASC model. So let us carefully summarize our results. While the ASC model may seem to provide a neat account of creation within the ASC, it gives rise to a rather peculiar story on the physical level, assuming constant speed of light. On that level, there are at least two remarkable features. And he says, one, the process corresponding with the fourth solar day of creation in the ASC model is effectively spread out over a period of billions of years for the observable universe. This does not align at all with the literal solar day as commonly perceived. It defeats the original purpose for which the ASC model was constructed, namely to uphold the plain reading of Genesis 1 in terms of the solar days. The ASC model, when interpreted in terms of plain physics, contradicts the very reading that it aims to defend. On that first argument, how would you respond to it?
Okay, what he's doing there is he's tacitly assuming that the Einstein synchrony convention basically is true. It's the true situation. It's the objectively correct synchrony convention. And what he's doing is he's saying, if you take my supposition that the Bible is describing God creating the universe in 6 days using the anisotropic synchrony convention, and you convert that to the Einstein synchrony convention, then looking at it from the Einstein synchrony convention, God's creating the farthest galaxies first, and then inward at the speed of light until you finally get to our solar system. And yeah, if you convert to the Einstein synchrony convention, that's true. But what I would deny is that the Einstein synchrony convention is somehow more true than the anisotropic synchrony convention. And by the way, Einstein would be on my side because he stated that in his own book on relativity. So he's tacitly assuming that the Einstein synchrony convention is somehow true. He's also tacitly assuming that the Bible's using the Einstein synchrony convention when it describes the creation of the universe. And that's the very point I'm making, is that no, that doesn't make any sense. God wouldn't use a convention that wouldn't be invented until, well, properly in the 20th century. And so I'm pointing out that under the anisotropic synchrony convention, God really did create everything in 6 days, and it's not a problem getting the light here. So he made several mistakes in reasoning there.
Right. And his second argument is this: as can be seen from the animation above, he's talking about this thing right here. He says, as can be seen from the animation above, the ASC model results in the revival of a geocentric view of the universe. It renders the whole universe as being having been created inwardly and geocentrically. This is remnants of the times when even respected theologians like John Calvin believed that the scriptures demand that people adhere to a geocentric view. See, for example, blog posts by Wyatt Hoot or whatever that is. While we are all thought that humanity had put the issue of geocentric to rest centuries ago, the ASC model indirectly brings it back to life in different form. So he's sitting there saying that the ASC revives the geocentric model. Is that what ASC is doing?
No, and that's borderline dishonest, his claim there, because the geocentrism was the idea that the planets all and the sun orbited the Earth. The other planets and the sun all orbited the Earth, and we don't hold to that, obviously. I don't think the Bible speaks to the issue of heliocentrism versus geocentrism, as far as I can tell. But I can get why he could maybe try to persuade people of that, because it's from the Earth's perspective that creation is designed. And again, he makes the same mistake of somehow tacitly assuming that the Einstein synchrony convention is the real situation and ASC is just phenomenological. I would reject that. And so he's saying, you know, if God really made the universe in 6 days by ASC, then when you convert it to the Einstein synchrony convention, then that has God creating inward and Earth's last. So, you know, Earth's kind of in the center of a finite number of galaxies. And by the way, the Earth might be near the center of a finite number of galaxies. That's not geocentrism in the sense that it was used, you know, at the time of Galileo. That's a different issue. The Earth may very well be near the center of a finite number of galaxies. We don't have any data otherwise. We don't have any data either way on that. So again, it's borderline dishonest. But it's the funny thing is, if you flip it and you say, well, no, the Bible is using the Einstein synchrony convention, and God created everything, you know, in 6 days by that convention, and you convert it to the anisotropic synchrony convention, then that means God is creating outwardly over billions of years. So either way, it puts the Earth as the focus of God's attention, but that's because the Earth is the focus of God's attention. God spent 5 of the 6 creation days working on the Earth, making it right for life. Day 4 is everything else in the universe. It takes one day to make everything else. Earth is special. And so if this person's criticizing me for claiming that creation is described from Earth's perspective, hey, guilty as charged. But I think that's because the Bible describes the creation from Earth's perspective. If he's claiming, well, that I believe that the Earth is special and deserves special treatment, I do, because this is the planet where God became a man and died for my sins. And that's awesome. He didn't do that on Neptune. He didn't do that in any other place in the universe. Earth is special. And so, and clearly from the Genesis point, you know, the creation of the universe is described in Genesis from Earth's perspective. That just makes sense.
The Bible says, I think it's in Isaiah, that God created the earth so it can be inhabited. So he created the earth for us. And then he also created the stars in the universe for us on top of that, because to give light upon the earth, like you said, and for time to tell the times and seasons and so forth. So so Earth is special, or the people in it are special for that purpose and that sort of thing. So it would only make sense that it would be from our frame of reference anyhow. All right. There isn't something else. This comes up sometimes, and I think Maddie brought it up. It's brought up in the biologos argument as I'm fixing the show. But some people bring up the idea that if ASC was true, then we would not be able to see stars being born, which is kind of an odd argument. It's like, okay, how's that disproved at ASC exactly? But I guess it's the idea of star being born, that it didn't arrive on day 4 the way, you know, the Bible describes. And so therefore the ASC model must be wrong because of that. Here I'm gonna share the screen real quick, because the biologos argument actually gives a diagram of a nebula that did that allegedly. See if I can find it. It might be down here. Yep, right. Nope. I think that's, yep, right here. They give a picture of the Eagle Nebula, which they claimed a star formed in. And I know that we talked about star formation theories and issues with that. And going back to that discussion, nobody's actually seen a star formed. Is that correct?
Correct. Yep.
So when they say that they've actually observed a star forming, like in that nebula or something like that, what exactly are they actually seeing?
So yeah, what they're seeing is a nebula. So it's a cloud of glowing gas, and there's stars in it. They do not see stars. They do not see gas collapsing in on itself, forming a star. No one's observed that. I don't think it happens. I'm not adamantly against it. The Bible doesn't say stars don't form, but at the same time, I'm very skeptical that they do, and we certainly don't see it. So if anybody said, "No, we see stars forming," they're either lying or horribly misinformed, because we don't see that. What they actually see are stars, and some of these stars are hot blue stars. Maybe not so much in the Eagle Nebula, but Pleiades, for example, have hot blue stars in them, O and B type stars, and or Orion's Belt, for example. People will see places where you have lots of O-type stars, and O-type stars cannot last billions of years because they're extremely luminous. They use up their fuel quickly. They can't last even 100 million years. They can't last that long. And so the assumption is they must have formed very recently. So they must be in a star forming region if there's a lot of them. So what they're really looking at is evidence for a young universe. And they're twisting it to say, well, this must actually prove that stars are forming. It doesn't. No one has seen a star form. They just haven't.
Right. We reached the end of the objections. I do have a final question on the objections. Is there anything that you would like to add that we might have left out that sometimes people raise up on what they believe to falsifying it? Now, you do make a distinction between ASC and ASM. ASM being the model that you've come up with, which shows that the Bible is using the ASC convention. So you do make a distinction between those two things. ASM is what is the model that you came up with, but the ASC goes all the way back to Einstein.
Mm-hmm. Yeah, and ASC is a coordinate system. And so when people say, well, I think I can prove the one-way speed of light, you're basically saying you can't use those coordinates. Well, I can use those coordinates. So you cannot refute a coordinate system. It's a coordinate system. It's like trying to refute the metric system. It's you can use the system or you can use some other system, but you can't refute a coordinate system because that's not what it's about. It's either useful or not, but you can't refute it. So when somebody thinks that they found a way to prove the one-way speed of light, I can almost guarantee you they haven't read any literature on the subject, because this was discussed. Einstein's theory, when it first came out, not everybody believed it right away. It wasn't until the eclipse of 1917 or 1919 that people started saying, oh yeah, maybe, you know, Einstein might be right. And people tried to refute him in the early part of the 20th century. And a lot of the folks that rejected the physics of Einstein also rejected the conventionality thesis, because Einstein held to that, and it's a consequence of relativity. And so there have been all kinds of different thought experiments that people have done to try to measure the one-way speed of light. And they always tacitly assume the Einstein synchrony convention when they do their experiment. There's a book on this, in fact, that people should read, and it's not written by a crazy creationist like me, so you can trust that it's good stuff. But it's a book written by Max Jammer, and it's called
Concept of Simultaneity.
Yeah, Concepts of Simultaneity, from Antiquity to Einstein and Beyond. Concepts of Simultaneity from Antiquity to Einstein and Beyond. It's a great book. And I would recommend, before anyone writes me, hey, I've discovered a way to measure the one-way speed of light, please read that book first, because it does a great job of summarizing. I only came upon that book recently, actually, only within the last few years, but it does a great job of summarizing a lot of the technical papers that I'd already read on this subject that were written in the early 20th, most of them in the early 20th century, and then a few in the later 20th century, including what I think is a devastating article by, or two articles by John Winnie, and another one by Wesley Salmon, who really shows that the convention can't be refuted. Now, the model that I proposed can be refuted. Potentially, it can be falsified. It's a model. I'm proposing that the Bible uses an anisotropic or visual, they wouldn't call it that, they call it a visual synchrony convention, because all ancient cultures inherently used that without thinking through necessarily the implications of it. But they, when you see something, that's when it happens. I'm assuming the Bible's using that. I could be wrong on that. I don't think I am, but I could be. And then I've made some other assumptions. I've assumed that gravitational time dilation is not a major component of the evolution of galaxies and such. So those things are subject to criticism. I've made some predictions, however, based on the anisotropic synchrony model, and including the fact that distant galaxies should be mature, they should not be clunky, they should have some of the heavy elements in them. These were things that I predicted that James Webb would detect. They're opposite the secular predictions, and you can look and you can find that my predictions were right on. Actually, so the anisotropic synchrony model is doing very well.
Actually, if I remember correctly, you actually made this in writing, and I actually heard someone else, and I can't remember who it was, that told me, and I don't know if it was Dr. Terry Mortensen when I interviewed. Someone said something about the fact that you made this in writing, and they're happy that you made this in writing. Mm-hmm. I don't know if they said it to me or something I read, but I remember them saying that they were happy you made this in writing. But you made these predictions on your website before they ever discovered them. Is that correct?
That's right. Yeah, that's right. Back in January 2022, I predicted what James Webb would detect. And then later and then I wrote a follow-up article basically saying, here's what James Webb detected. And guess who was right and guess who was wrong?
Were they surprised when they found that out, when the James Webb detected it?
Yeah. And the funny thing is, I even predicted what they would say when their predictions failed and when mine were right. I predicted that they would say things like, the James Webb Space Telescope discovers that galaxies formed much earlier than previously thought. And since then, I found several headlines that say just that, or several even peer-reviewed articles that say just that. So I not only predicted what James Webb would detect, I predicted how the secularists would respond when their predictions were wrong. And in all cases, I was right, not because I'm so great, but because I start with Scripture. If you want to get the right answer, start with the Bible.
I have a question. Sometimes scientists will show pictures of galaxies moving away to show that the universe is expanding. would you argue from the ASC perspective that that's happening now, and that's why you see them moving away? How would the people who's using the ESC see that? Because if the Big Bang was true and the universe was expanding outward, should we see the galaxies going toward each other? And the reason I'm asking that question is because somebody had actually, the first question that they asked in your debate with Hugh Ross, moderated by Frank Turek, was that very question. And he wasn't trying to ask the question to get anybody. It was an actual legitimate question, I thought. Why do we see these galaxies moving away? Why don't we see it going backwards, going toward each other? So how would you explain that? Would you say that the reason we do this is because of the ESC, or I mean, how would you answer that question? I don't think they gave you the opportunity to answer it. I think that Hugh answered it, and he actually contradicted what he said earlier. But how would you answer that? Do you know what I'm talking about? Do you remember him asking that question?
I don't remember specifically. I'll have to, So we don't actually see galaxies moving. I mean, we can measure the Doppler shifts of the stars. We know how the stars are moving within the galaxy because they're Doppler shift. We do see proper motion in our own galaxy. We can see stars near the core that are actually orbiting. But in terms of galaxies actually moving away, we don't actually observe that. That's inferred from their redshift. And I think that's the right interpretation. I do think how do I say this? I think the distance between us and just about any given galaxy, except some very nearby ones, I think that distance is increasing. And the farther away a galaxy is, the faster its distance is increasing. So galaxies do seem to be moving away from each other. The only difference between, remember, anisotropic and Einstein synchrony convention, they're both describing the same underlying reality. So they don't affect what's actually happening. It's just a question of how we describe when something's happening because of the way we synchronize clocks. So under the anisotropic synchrony convention, we would say the universe is expanding now, or at least galaxies are moving away from us now. In the Einstein synchrony convention, you could say galaxies at least were moving away from us and probably still are because of, well, conservation momentum. Stuff that's moving away tends to continue to move away. Gravity would tend to slow it a little bit, but we think that the gravity of all these galaxies is insufficient to stop them, let alone reverse that expansion. So I think under each convention, you would say the universe is expanding.
I don't want to get into the Big Bang Theory because we have a video on that talking about that. But I've often heard like Hugh Ross or something will say that we can look back in the past and you actually see, the Big Bang and that sort of thing. But as far as I could tell, that's not the case. We don't actually see. Now, of course, we'd probably argue because Big Bang didn't happen, but he claims that we could see that. So under ESC, assuming ESC, would he be right? If the Big Bang happened, then we should be looking back in the past where we're actually seeing the universe get born or something like that, or something close to that, like with galaxies forming and that sort of thing.
Yeah, and that's why the James Webb Space Telescope results were so devastating to the secularists, because that's not what we see. If the Big Bang were true, and if you're using the Einstein synchrony convention, and you kind of have to for the Big Bang to make any kind of sense, then when you look at the universe and the most distant regions of the universe, you're seeing them as they were in the distant past. And the idea is the James Webb Space Telescope was supposed to be able to look at such a great distance that the galaxies basically stop, because there shouldn't be any. It's supposed to take 400 million, 500 million years for the earliest galaxies to form. And James Webb can see farther than that. It can see farther in space than that would correspond to a time earlier than that under the Big Bang paradigm. And so the fact that it didn't, and that it in fact saw galaxies, they should stop around redshift 14. Redshift 14 is how much the light stretched. That corresponds to a distance in the Big Bang view that corresponds to a time of about 400 or 500 million years after the Big Bang. But we see galaxies beyond that. We see galaxies. I've seen some papers that say James Webb's detected galaxies out to redshift of 20. And so that was not expected by the Big Bang supporters. It is something that I was expecting. I didn't give a quantitative limit, but I just said I think they'll go out farther than the Big Bang predicts. So so once again, the evidence is very consistent with the creation view, and my model in particular, although it doesn't exclude other creation models, but it's not consistent with the Big Bang.
Right. All right. We came to the end of our discussion. Do you have any final thoughts on this particular subject matter before we leave?
Well, I just point out that you know, I've proposed an explanation for distant starlight that is consistent with known physics and takes into consideration the way the Bible it tries to communicate to all persons at all times. It is a model. Please don't hang your faith on my model or any particular model other than the Bible. The Bible's not a model. It's the foundational historical truth that makes models possible. I do want to point out, though, that my model has made successful predictions so far, predictions that were contrary to the secular expectations. And so in terms of science, it's good science. You got a model that accounts for things. It makes correct predictions, specific correct predictions about what James Webb would detect, and et cetera, et cetera. So I think we have a good model there, but ultimately we know that God's word is true by virtue of the fact that it's God's word. And there have been countless times throughout history where the secular experts of the day thought the Bible was wrong, and they now have egg on their face because we know it's right in every area that it's been tested. It's been demonstrated to be correct, and in fact, it gives us the apparatus by which we can test other things.
All right, it has been great having you on here, Dr. Lisle. It has been exciting as always. I always learn something new whenever you come on and have a discussion with me. Sorry it took so long for us to have this discussion, but you've been pretty busy lately. And it's a good busy. I mean, like you said, it's good based on what you're doing and so forth. But I enjoyed it as usual. But it'll probably be a long time before you'll be able to get back on there. Heard you're fixing to go on the road again, I think. Is that right?
Yeah, got a lot of stuff coming up, but that's okay. I mean, it's all good. It's all good.
Right. I enjoy it. I really did. And as you know, I've been wanting to have this discussion for a while on ASC. I had a discussion a few weeks back with Simon Turpin on responding to John Walton, who's a theistic evolutionist. So I've had a lot of good conversations. I had one with Dr. Terry Mortensen. I had one with Eric Hovind last Friday. So yeah, I had a lot of good conversations, and I really enjoy having these discussions. This Genesis series that I'm doing is by far the best thing the biggest thing that I'm doing on this channel this year, and I'm still in chapter 1, but I think I got like 3 more videos I want to do, and then I'll move on to chapter 2. But it is great. I can't wait to get chapter 2 because we'll be talking about creation versus evolution type deal. A lot of these topic matters you have discussed or something. As much as I would love to have you on for other topic matters, you're just kind of like really, really busy right now. So I'll give your assistant a rest. But anyway, but I do enjoy it, and I guess probably a while before we have another discussion. But take care. God bless. Be careful, and I guess anything else you want to say, or
thanks for having me on. God bless you too.
Thank you. All right, we'll end it here. Thank you for watching Apologetics 101. We had a great discussion with Dr. Jason Lisle on the so-called distant starlight problem. As we can see, when relatively properly understood, it's not really a problem at all. Not really. It just people assume the rigidity of time, passing of time, the same, as it is today. But it's not the same. Einstein discovered that different things can affect time.
gravity, distance, speed, all these things can actually affect time. And so as a result, it's not always as what we would think it is in modern Newtonian thinking. Whether instead there are certain conditions that can affect the way time is and how long something takes, and we can get light here in the biblical time frame. And but this has been a joyous discussion. I did forget to mention one thing, actually a couple things in the interview. Right before I actually discovered, he actually answered this in his book, but right before he said that, I was sitting there thinking, well, what if someone has this idea of using, radios or cell phones to signal to the other person who's synchronizing their clocks and tell them that. But he answers this in his book. He says that, in his book, he said that would technically work if you actually knew the speed of radio waves. Well, how fast does radio waves travel? Speed of light. So we just need to know the one-way direction for the radio waves, which is the one-way speed of light. But if we knew the one-way speed of light, we wouldn't need to measure it. That's the thing that we're trying to figure out. So I thought that was good. Another one is that I didn't really talk about the horizon problem. Now, we did talk about the horizon problem in when I did a discussion with Dr. Jason Lisle on the origin of the universe. So watch that if you want a more detailed discussion of that. But relative to this discussion, the horizon problem kind of makes the whole argument self-refuting when someone tries to use the so-called distant starlight problem at us, because the Big Bang has its own light travel time problem with the horizon problem, because they can't get light from one side of the universe to another to be touching in order to create kind of a thermal equilibrium, because there are different points in space that should be at different temperatures if the Big Bang theory is true. And it turns out that it's all one even temperature, an average of 3.75 K, I think, is how they measure the temperature of the entire universe. And so this would actually make the so-called distant starlight problem self-refuting as a result. And I forgot to mention that as well during the course of the interview. But other than that, everything went really smoothly. I really enjoyed having that discussion with Dr. Jason Lisle, joining us again on Apologetics 101 on the Genesis series, because we will be doing, I plan on having 3 other videos of the Genesis series for chapter 1. One will be on the Rakia. I want to have one on, whether the Earth has a solid dome, around it. That's something, or is believed to have a solid dome around it. This is something that the law of theistic evolutionists bring up. So I want to have a video on that. I don't know if I'm going to do it presentation or interview. Haven't decided that yet. And if I do decide to interview, I don't know who it is that I'll be interviewing. And the second one, I would like to see Simon Turpin come back on here again to discuss whether or not if Genesis 1 through 11 is myth or mytho-history. And I would love to have him on there to have that discussion, because he seems to be well knowledgeable in the subject. And but nothing's set in stone. I haven't talked to him or nothing. So we'll have to see and play it by ear. A third interview I want to have is over Genesis 1 through 11 as historical narrative. I would love to have Dr. Jonathan Safrati on here for that discussion. His commentary on Genesis 1 through 11 has been a big inspiration for me on this commentary series and on my YouTube channel. And so I would love to have Dr. Jonathan Safrati on here to have that discussion. Again, nothing set in stone. I haven't talked to him or nothing. So again, we'll have to play it by ear and see what goes on. But please join me next time, and keep in mind to stay in the know. And this is Apologetics 101 signing off.